Hey there, folks. Back here with another video here where we are still studying application of the derivative, and we are still looking at functional analysis, going just a little further into the calculus of functional analysis, folks. And so far we've kind of explored critical points, intervals of increasing and decreasing, inflection points, intervals of concavity, and have spent some time on absolute extreme values. We're going to finish up here looking at the case for local extreme values. All right? These are, I should say, absolute extreme values can be local extreme values, right? And local extreme values can be absolute extreme values, but they're not necessarily both the same. Remember, absolute extreme values are extremes that are found on the range of our function. They describe either the largest value or smallest definitive value found in our range. If those values are positive or negative infinity on the high or low end, those are not, then we don't have absolute maximums or absolute minimums where we have those infinities. However, with local extreme values, where we differ is that we are not necessarily the largest or smallest value in the range. We just happen to be the largest or smallest dependent value of the function relative to our neighbors, right? Relative to the values around us in the graph. All right, let me bring up my notes here. Talk a little bit about local extremes, right? We say for y equals f of x, the local extreme values of f describe the locations in the domain where the dependent value of our function is the largest or smallest value relative to its location in its domain, right? Relative to the location in the domain of the function, we are the smallest or largest value. We may not be the smallest or largest value overall, but relative to the location we are. By definition, right, for y equals f of x, the local maximum values of f occur at x equal to c. If f of c is the largest dependent value of f for all x in some open interval containing c, and similarly, the minimum values of f, I should be a little bit more specific here, the local minimum values of f occur at x equal to c if f of c is the smallest dependent value of f for all x in some open interval containing c. We only have to be the largest or smallest value in some open interval around our value where we see this extreme value, as opposed to being the largest or smallest value in our entire domain. That is where we do see some difference in the two by definition. Now, if we say here, in other words, f of c is the local extreme value of x if it could be an absolute extreme value in some closed interval, right? Where c is somewhere in between the boundaries of a and b, right? What this does also can be interpreted as is, if we think about a local extreme value, it could be an absolute extreme if it was defined itself inside of a closed interval. Right? We could have it become a absolute extreme value. As for determining local extreme values, there are two procedures involving derivatives. And they're referred to as the first and the second derivative tests. They aren't necessarily in any particular order by those names of first and second. What first and second describes is the fact that they involve the first derivative or the second derivative of our function in the test for local extreme behavior. Right? That is where they get their names for first and second derivative test. The first derivative test uses the first derivative, and the second derivative test uses the second derivative. And The first derivative test examines the intervals of increasing and decreasing behavior before and after a critical point, whereas the second derivative test is actually going to analyze concavity at that critical point. If you remember, the first derivative will tell us where we're increasing or where we're decreasing. And what we'll notice about extreme values locally is that they are in between intervals where we're increasing and where we're decreasing, or where we're decreasing and then we're increasing. Right? So the first derivative can be used to help us determine those locations where that change in increasing and decreasing behavior occurs. If you remember, the second derivative allows us to analyze concavity of our function. And what you will notice is if you're in a region where you are concave down, at the top of that region, right, or at the top of the function in that region, you will find a local maximum. And if you are in a region where you're concave up, at the bottom of that region, right, or on the bottom of the function in that region, you are going to find a location where you are a local minimum value. And it uses the concavity at a critical point to determine whether or not what we have at that critical point is a local maximum in the case for concave down, or a local minimum in the case for concave up. It's the first and second derivative tests. Now, the first derivative test says you do have to have a function that is continuous and differentiable on some interval containing a critical point x equal to c. All right? And if you do have a function f that is continuous and differentiable on this open interval containing c, on some interval containing c, there are three results that could happen around this critical location. Three results in terms of behavior. And what we can see happen for f at that critical point is that we could see it describe a local maximum value. If f is increasing before x equal to c and decreasing after it, at f of c we could see a local minimum value. If f is decreasing before x equal to c and increasing after it. And lastly, you could have neither of those two things occur, right? If f of c remains either constant or constantly increasing or constantly decreasing on that interval that contains x equal to c. And one additional thing to note is that f doesn't necessarily have to be differentiable at x equal to c in any of this setup. And perhaps I'm going to move that in here. It feels just out of place down there. So I'll say that there instead. All right. And why that would be the case is because if you think about something like an absolute value function that forms a V shape, at the peak, you're not going to be differentiable. But you will have a local maximum there because you will be increasing before that value and decreasing after it. Right? So we do have to have that one condition. Other than that, we need to be continuous over that interval where we're finding that maximum or that minimum value. Right? If we put this just into some other words with a bit of an illustration, because I haven't really illustrated these yet. As I was opening here, I said, I need an illustration, and maybe I'll go back in and add one, or maybe I'll go back in and add this illustration without the details, and I can do that. Without some of the details, maybe take out these intervals of increasing and decreasing. Right? And in fact, I'll do that here at the end. But in other words, the first derivative test examines the intervals of increasing and decreasing behavior around a critical point. We're looking at the increasing and decreasing behavior in this graph around these critical points. Now, we will note these are local minimums and maximum values. This is what we see describe local mins and maxes. They are not the overall max, the absolute maxes, or the absolute minimum values. This graph does get larger than this local max, and it does get smaller than this local minimum, right, when we analyze this graph. But these are locations that are unique to the fact that the graph is behaving a certain way as it moves through that location. It is changing at this location from decreasing in its behavior to increasing in its behavior. And it is changing at this location from increasing in its behavior to decreasing in its behavior. These local minimums and local maximums seen here in this graph are playing the role of the boundaries between these intervals of increasing and decreasing. So if a function is continuous over these intervals of increasing and decreasing, at those intervals, the boundaries of those intervals of increasing and decreasing is where we will encounter some local extreme values. And we see that here in this illustration. Let's look at an example. I do kind of jump out of the polynomial realm for this one. And I say, let's consider the function f of x equals x times e to the x. If we take notice, its first derivative through a little bit of product rule will give me x e to the x plus e to the x, which can be factored into e to the x times x plus 1, which does exist everywhere. E to the x exists everywhere, and so does the other factor x plus 1, the linear function. And what we notice is that at x equal to negative 1 is the only place that f prime of x would be equal to 0. It's the only one of these two factors that will cause the dependent value of f prime of x to equal 0. E to the x is always positive. It's always bigger than 0. But x plus 1 is equal to 0 when x equals negative 1. So that implies x equals negative 1 is a critical point in the graph of this function. All right. Now, if we go further and we analyze the behavior for the intervals of increasing and decreasing around this critical point, what we will note is that, as I had said, e to the x will always be greater than 0. So the only factor that's going to cause this product to be less than 0, to be decreasing, or greater than 0, to be increasing is going to be this factor x minus 1, x plus 1. And what we can note is x plus 1 is less than 0 when x is less than negative 1. And we can find that by solving that equation, that inequality. Set x plus 1 less than 0 and solve, and you will get x less than negative 1. And similarly, it's greater than 0 when x is greater than negative 1. Set x plus 1 greater than negative 1, and solve, you will get x is bigger than negative 1. Implying f is decreasing then on the interval from negative infinity to negative 1 and increasing on the interval from negative 1 to infinity. And since f is decreasing before x equal to negative 1 and increasing after x equals negative 1, at x equal to negative 1, we must have a local minimum value from the first derivative test. The local minimum value must be f at negative 1, which equals negative 1 over e in value. And if we focus our attention on that location in our graph, this is the graph of the function x e to the x. And we do see that at this location where x equals negative 1, we are decreasing before that location and increasing after it. Which means at that location must be where we have a local minimum value in its graph. Plugging that negative 1 into our function, we will end up with negative 1 over e. And that is the value seen here as the dependent value on the y-axis. It is the smallest dependent value relative to its location. If I was to think about this being on this closed interval where this graph may not continue off to the left or to the right here, it would be the local minimum value. It would be the absolute minimum value on that closed region. What helps to make it a local minimum? That and that it's decreasing before that location and increasing after. Let me also note the concavity there. At that location, the graph is concave up. Meaning that, yes, if you would have this be a critical point in this region where we're concave up, then that must be a local minimum in that region. And that's what the second derivative test looks at, folks. The first derivative test examined these intervals of increasing and decreasing behavior around our critical points. Now, we're going to consider what's the concavity. All right, that's the second derivative test. The second derivative test says consider y equals f of x and assume f prime of c equals 0, where f double prime of x is continuous on some open interval containing x equal to c. Yes. Yeah. F prime of c is going to equal to 0, where f double prime of x is continuous on some open interval containing x equal to c. And there are some conditions there for that setup. You do have to have a slope of the line tangent to the curve at this location be 0, and that is what we see going on here in this graph. And the function itself needs to be continuous at that location. All right, I'm back. I had to take a quick little break, and one of the things I wanted to add was just the graph earlier, and I went ahead and put that in. I'll show you that here in the end. But let's see here. Yeah, there are some conditions for the second derivative test to be, to run. You do have to assume that the slope of the line tangent to your curve at the critical point is 0, right? And f double prime at x, right, is continuous on this open interval, right? You do have a second derivative that is continuous on that interval, meaning it's what, differentiable in a sense, right? Well, there are 3 results for this test that could occur, right? And that would be that f of c is a local maximum value of f when the second derivative of your function at that critical point of c is less than 0. And that is accurate. You do have a maximum value when the second derivative of your function at your critical point excuse me, is less than 0. All right. Remember, being less than 0 means you are concave down. And if you were concave down for your second derivative, you have a local maximum at that critical point given by your first derivative up here at the tip top. Likewise, if f of c is a local minimum value of f when the second derivative of our function at that critical point is greater than 0. That highlights that we are concave up, and at the bottom of that concavity is where you will find your local minimum value. Now, the one drawback to the test, because it is a convenient test, it is just a matter of finding your second derivative and substituting in your critical point, right? And analyzing the result compared to 0. However, there are times that it does equal 0, and at those times you do have inconclusive behavior. You have an inconclusive result from the test, and you have to try something else. You might be forced to go back and try the first derivative test, right, to analyze that behavior. So the first derivative test doesn't have inconclusive results. It's the second derivative test that does. So there are times where if you try it, it may give you inconclusive results, and you just have to be prepared for that and have to go back and use the first derivative. And if you have the second derivative, chances are you already also have the first. Just take note. Let's consider this graph above. Again, we note, how can we see that this is concave up here at that value of x equal to -1? Well, careful. Let's first of all just put this in other words. Here's my analysis of concavity, as we've kind of already gone through and described this situation, where we are concave up. Now, first of all, this is the same graph we had earlier. It is actually the graph that I included right at the beginning here. Right after we defined local extreme values up here earlier in the notes, I went back ahead and put back in this graph down here. This is the same graph illustrated in both of our both of our setups for the first and second derivative tests. In the first derivative test, we analyzed increasing and decreasing around these critical points. What the second derivative test is now going to do is analyze concavity, which means in the graph you will find your inflection point or have your inflection point illustrated. That would be right there, where we can see a local minimum will be in this region here where we are concave up, and we are concave up here where in that region we can see that at C, we certainly have a local minimum value. And here at this C, in this region where we're concave down, we do have at C a local maximum value. That's what the second derivative test for local extreme values is looking at. It's testing the concavity of our function at this location. If it's concave up, it's a local min. If it's concave down, it's a local max. How do we know when it's concave up? Well, its second derivative will be greater than 0. How do we know when it'll be concave down? Well, that will be when its second derivative is less than 0. As the test tells it, tells us what we should expect. Now, let's go back to our example. Let me separate these. This is part of the definition. And let's go back and consider our example here. We knew our first derivative was e to the x 1 plus x. And that gave us a critical point at x equal to -1. So we now want to test this x equal to -1 in our second derivative of this function. If we note through a little bit more product rule, the second derivative of this function is e to the x times 2 plus x, where if I substitute in -1 into that function, 2 plus -1 is going to be +1 in value, and I'll have 1 over e, because e to the -1 is 1 over e, times +1, which is just going to always be greater than 0, which is a positive value, greater than 0. So since f double prime at -1 is greater than 0, from the second derivative test, we know that a local minimum value must be occurring at that location. Right? We know f at -1, right, which we said earlier is equal to -1 over e, right, is a local minimum value of f. And we'll state it that way. All right. The same result we had earlier, but here determined with the second derivative test. We went ahead and performed the second derivative test. And notice it's a little quicker in its result. You just have to substitute in your critical point into the second derivative. Find your second derivative, substitute in your critical point, and evaluate it next to 0. Compare it, right, to 0. Analyze its behavior in terms of sign. Is it positive or negative? Here it's positive, so that means we have a local minimum at that value. Let's do one more example. I always like to give you more than one example if I can. So here's another. Here's a rational function. Right? We might consider f of x equals x squared plus 5 divided by x minus 2. Through a little quotient rule, we can find our first and second derivatives. Now, I'll leave you to find those on your own, but if we do find them, from quotient rules, we end up with these two results in their factored form. F prime of x is equal to the ratio of x plus 1 times x minus 5 over x minus 2 squared. And the second derivative actually simplifies into 18 over x minus 2 cubed. Apparently there must be a factor of x minus 2 in there that cancels. Perform some quotient rules and determine those results. Factor and you'll get these results. These are nice forms. Here I can see f prime of x and f double prime of x do not exist at 2. All right. What must be happening at 2 must be a vertical asymptote. And we do see that as the truth here up in this graph at x equal to 2. We have a domain concern where we will expect a vertical asymptote. Now furthermore, right, the first derivative does have a numerator that factors into x plus 1 and x minus 5, which if I set those equal to, if I set f prime equal to 0, right, only equals 0 when the numerator equals 0. And when does this numerator equal 0? Well, when these two factors alone equal 0. So that's going to lead me to x minus 1 and x plus 5 as potential critical points along with that value of 2. Now at 2, again, we know there's a vertical asymptote. But we can analyze the behavior of our function at -1 and 5. And what we can do is we can see what does f double prime give us at -1. And if I take -1 and I substitute it in here for fx and f double prime, -1 substituted into this denominator will become -3 when we subtract 2. Cubed will become -27. And 18 over -27 will simplify to -2/3, which is less than 0. So since f double prime at -1 is less than 0, that means at x equal to -1 from the second derivative test, we must be concave down and be a local maximum value at that value of x. Right? From the second derivative test, f at -1 is a local maximum value, and we probably should evaluate what that is. Let's go ahead and point out that that is, if we plug in -1 up here, that'll be 6 over, what is that, -3? So 6 divided by -3 is going to equal -2 in value. F at -1 equal to -2 is a local maximum value. Now we should see that in the graph later here. Right? And then note at x equal to 5, we also had a critical point. Well, first of all, let's say here we get the same result from the first derivative test. If we go back and we analyze our first derivative, right, for values smaller than -1, this will be negative, and this will be negative. These two factors in the numerator will both be negative, which means if we multiply them, they'll be positive, and they'll always be over this value that's also going to be positive, because any quantity squared will always become positive. So if x is less than -1, you'll have negative times a negative, which is a positive over a positive. So f prime would be positive. You would be increasing before -1, which is what you would expect with a maximum. You would be expecting the increase before there. and it should be decreasing after it. So if we're smaller than -1, let's say we're between -1 and 5, right? This quantity is going to be positive, and this will still be negative. That'll lead us to a negative in the numerator over something that's always positive, and then that would lead us to the case for decreasing. And again, we would have increasing before, decreasing after, so it correlates with that idea that we have a local maximum at -1 given by f of -1, which equals -2. Right? It correlates with this result. Second derivative test is a lot quicker in its analysis. If you can perform it with the correct second derivative, right? That's the one other problem, is you also have to get the second derivative correctly. It's just a matter of evaluating it, second derivative at your critical point. Right? Just plug in 5. We can see here, when we plug in 5, right, into our second derivative, it is going to be 5 minus 2, which gives me 3 cubed. I will end up with positive 2/3. 18 over 3 cubed is 18 over 27, which simplifies to positive 2/3, which is greater than 0. That says that f of 5, I must have a local minimum value. And again, what is that? It is going to be, let's go back up and look at function f. Oh, overshot that. Plug in 5 here, you will get 25 plus 5 is 30 over 5 minus 2 would be 3. So 30 over 3 would result in 10. So f at 5 equal to 10 must be a local minimum value of our function. And what we'll notice is the first derivative test will give us a very similar result. And we can see all this graphically. If we bring this picture up into our graph, here's our graph, and we can see this behavior. This is a rational function. So you're going to see a little unusual behavior in terms of where we're maxing and where we're minimum, and vertical asymptotes and the like. Here's our vertical asymptote at 2 that we found as a critical point. And then down here is our critical point at -1, where we saw a local maximum value. Right? We saw that equal the value of 3, or -3, which is over here equivalent to that location on our y-axis. And then here is at x equal to 5 is also where we saw another critical point. And there we had a local minimum of 10. And that is the local minimum here in our graph. We can see we're increasing before this one and decreasing after it, as our first derivative test would tell us. And at this one, we're decreasing before it and increasing after it, which is what our first derivative test would tell us. This is local extreme values, folks. Neither of these values would show up as absolute extreme values. You have to perform either the first or second derivative tests, analyzing your critical points here to determine that extreme behavior. All right. This was the case of this rational function. And we did this for the case of x times e to the x. Second derivative test analyzes concavity at these critical points. Where you're concave up, you're a local min. Where you're concave down, you're a local max. And first derivative test analyzes behavior of increasing and decreasing around these critical points. Where we're decreasing before and increasing after, we're a local min. And where we're increasing before and decreasing after, we're a local max. Local extreme values just being locations in our domain, where if we were to consider just this location in some open interval, it would be a local minimum in that interval, which would be true, or even a closed interval, some interval. And if we considered this just in some interval, right, just focused our attention to this region where I'm circling, it would be a local maximum, or it would be an absolute max. So there we must have a local max. Right? And we have the first and second derivative tests to be able to actually find those locations. All right. Folks, that is functional analysis. Those are all the little parts that calculus provides us with. It all involves analyzing slope of the line tangent to the curve. Being able to analyze that first derivative, slope of the line tangent to the curve, and having it give us information about where our function is increasing and decreasing, develops into intervals of increasing and decreasing, which then we saw bring about concavity, because where we're concave up or down is where that slope of the line tangent to the curve is increasing or decreasing. And then putting it all together, we can use it to help identify absolute extreme values on closed regions, or help identify local extreme values on any region using the first and second derivative tests. What we're going to come back to, folks, is we're going to come back and look at kind of putting it all together in summary with some of our college algebra knowledge, right? Go back to some of our college algebra knowledge and be able to put together some really precise graphs, being able to indicate all the key features. Intercepts, X and Y, end behavior, asymptotic behavior, and even extreme and intervals of increasing and decreasing, inflection points, all that good stuff. We're going to put it all together in a nice summary, folks, for a few examples. So that will be the next video I have coming out, folks, and I will see you in that next one.